In this video, we're going to look at a matrix and we're going to decide whether the matrix is diagonalizable, and if it is, we're going to find the diagonalization of the matrix. Alright, so the matrix we're going to look at is the following matrix. A given by, it's a 3 by 3 matrix whose entries are 0, minus 9, 0, 1, 0, 0, 0, 0, 1. As we said, we want to decide whether this matrix is diagonalizable or not. And if it is, we want to find the diagonalization. What does this mean? Let me remind you that a matrix is diagonalizable. That means that there is a matrix P, an invertible matrix, such that P inverse times A times P equals some diagonal matrix D. From the theory of diagonalization, we know that this is equivalent to having, well, the fact that this is equivalent to having this is not much of a deal. We just multiply both sides by P. So this is equal to having this equality together with P being an invertible matrix. And then this second one, we know from the theory, is equivalent to having the columns of P being, so let's actually write these equivalences out. The columns of P being eigenvectors for A, and the entries of the D matrix, the diagonal matrix, being the corresponding eigenvalues in the same order. To be more precise in what I write, let me put here also that these diagonal matrix, and here I need to add that as well. You see, the reason why I'm not saying in the first line that P is invertible is because that's evident from the fact that we're using P inverse there. And then in the next step of simplification of, or rather reformulation of what this all means, in the next step we're going to say this means that P is given by some column vectors k1 up to kn. In this case, it's going to be 3 of them, because we have a 3 by 3 matrix, k1, k2, k3. And the D is the diagonal matrix lambda 1, lambda 2, lambda 3, with all the other entries being 0. That's how we can represent it, with those large zeros at the bottom and above the diagonal, with having the equations ak1 equals lambda 1 k1, ak2 equals lambda 2 k2, ak3 equals lambda 3k3. And one additional requirement is needed here, the invertibility requirement, which translates to the k vectors being linearly independent. So k1, k2, k3 are supposed to be linearly independent. Okay? Now, linear independence of the k vectors guarantees that none of them can be the 0 vector. If one of them was the 0 vector, then the sequence of the 3 vectors wouldn't be linearly independent anymore. And since none of them is a 0 vector, and we also have these equations that hold, this means, of course, is that each k is an eigenvector for A, for the matrix A, and then each lambda in the corresponding column of the diagonal matrix is the corresponding eigenvalue. Why did we do all the talking here? Well, because now we know, and we knew that before, we just recalled it here, that to diagonalize a matrix is the same as to solve the eigenvalue problem, and more specifically, for a 3 by 3 matrix, to diagonalize it, what we need to do is to find 3 linearly independent eigenvectors and the corresponding eigenvalues. And then we can arrange them into a matrix P and the D respectively to get the diagonalization. Alright, so let's do that. So let's apply our knowledge of how to solve an eigenvalue problem to find the matrix P and the matrix D, in other words, to find the eigenvectors and the eigenvalues. The first step is to look into the characteristic equation, right? I might as well put it in here. Maybe I'll make a certain separation between these two sections. So what is a characteristic equation? It is this equation. The determinant of A minus lambda I equals 0. And so that matrix there is the A matrix with the lambda subtracted away from its diagonal entries. So we'll have minus lambda, 1 minus lambda, then minus 9, 0, 0, 1, 0, 0. That determinant needs to be 0. Okay, let's simplify this and see what it gives. So we can then write that this is a characteristic equation that we get here. Minus lambda times 1 minus lambda, and then minus from that 0. Just to clarify, what I'm doing here is that I'm multiplying minus lambda with the determinant of this 2 by 2 matrix. But of course, minus 0 doesn't change the value, so we can end it off there. So it's minus lambda times the determinant of that 2 by 2 matrix, which is this. Then, from that, we have to subtract minus 9 multiplied by the determinant of the matrix excluding the middle one, the middle column, and that's going to be 1 times 1 minus lambda minus 0. And again, 0 doesn't have any effect. And then we have plus 0 times something. We don't even have to worry about what that thing is, but in fact it is even 0. So the characteristic equation is given by equating this expression to 0. Okay, so then let's simplify this equation. And here is an important thing we need to keep in mind. We could simplify it directly, but it's actually easier to factor things out. You see, 1 minus lambda can be factored out here. So when we factor 1 minus lambda out, we'll get 1 minus lambda times. And then we have minus lambda squared, which is, minus lambda times minus lambda, which is lambda squared. From that, we subtract that 9 thing there, but it becomes plus now, because there were 2 minuses. So it's lambda squared plus 9. And the 1 stays there and drops out. So that's equals to 0. And of course, after this presentation, perhaps we can give a more explicit presentation. 1 minus lambda times lambda plus 3 times lambda minus 3 equals 0. And so after this presentation, we can see exactly what the eigenvalues are. And now we have to give them a certain order. And we will keep track of that order later on when we put them in the diagonal matrix, because the order for the entries in the diagonal matrix should correspond to the order for the columns of P. So let's write them in the order, any order we select now, but later on we stick to that order. So lambda 1 equals 1, lambda 2 equals, so I'm just going to follow the order that it appears the way I wrote this thing out here. Lambda 2 equals minus 3, and lambda 3 equals 3. So these are supposed to be the eigenvalues of the matrix A. Now what we need to do is for each eigenvalue to find the corresponding eigenvectors. Do I need to do that in order to conclude that the matrix will be diagonalizable? Can I not tell already from here that the matrix is diagonalizable? From the fact, namely from the fact that we got 3 different eigenvalues. can I say now that I will be able to find 3 linearly independent eigenvectors by having 3 different eigenvalues? It turns out that we can, because it turns out that if there are 3 different eigenvalues for a 3 by 3 matrix, then the corresponding eigenvectors are all linearly independent. So if the question was asking us to figure out whether the matrix is diagonalizable or not without finding the diagonalization, then by seeing that there are 3 separate eigenvalues, we could already know that the matrix is diagonalizable. And so we wouldn't have to find the eigenvectors. But when the request is to find the diagonalization, this is not just finding the matrix D, but it's also finding the matrix P. And you can see from here, it's impossible to express P in terms of A and D alone, right? So we will have to go through the route of finding the eigenvectors, and hence the diagonalization. But just for determining whether it's diagonalizable or not, we will already determine that the answer is yes, because there are 3 different eigenvalues, since the different eigenvalues are going to give rise to linearly independent eigenvectors. Now, a nice geometric way of seeing why different eigenvalues give rise to different eigenvectors is the following. That imagine that wasn't the case. Sorry, I'm not sure if I said it right. Why is it that different eigenvalues give rise to linearly independent eigenvectors? So imagine it's not the case. Imagine, let's say, that the third vector here, k3, is linearly dependent on k1 and k2. It means that the third vector would be a linear combination of k1 and k2. But now remember, what's the geometry of eigenvalue? By the linear map corresponding to the matrix, k1 gets stretched by 1 factor, k2 gets stretched by the -3 factor. And if the 2 vectors get stretched by different factors, so k1 will get stretched by a certain factor, k2 gets stretched by a certain factor, then their linear combination, let's say their sum, for example, for simplicity, but it applies to any linear combination. If the factors by which they get stretched are different, then the linear combination is no way is going to get stretched. It's going to move away. The angle is going to change. Like, for instance, if I was keeping one fixed and stretching the other one, you see the sum is going to change. The vector is going to make that angle with the original one. The only way for this vector to also have gotten stretched without changing the angle is for the 2 vectors that constitute that linear combination, for them to have gotten stretched by the same factor. So that's the geometric explanation. Why is it that for different eigenvalues, the eigenvectors will be linearly independent from each other? Okay, now coming back to the problem of finding diagonalization of the initial matrix. Now that we have the eigenvalues, we want to find the eigenvectors. And so let's do that. I'm going to go back here to copy this down, because this will be used for writing the system of linear equations out of the eigenvectors, out of which the eigenvectors will be produced, right? So let's look in each case, for each lambda. So for lambda equals for lambda equals 1, the system is this, and when lambda equals to 1, the system becomes -1, -9, 0, 1, -1, 0, 0, 0, 0. what eigenvector does it produce? Well, from the third line, we see that there is no restriction on k3, so that can be any real number, except 0 if I'm interested in eigenvector only. The second line is going to give some dependence between k1 and k2, right? But the first line is going to give a different dependence. So here, if I multiply both by 1, or maybe I want to do row echelon to simplify things, I could do that. So I could just add these two. I'm going to get, if I add these two, maybe I'm going to go through that approach, since that's a more canonical way that applies to arbitrary matrices of arbitrary difficulty, rather than using ad hoc explanations that only would apply in this specific case. So the second row will be 0, and just adding them will get -9 plus -1 is, what is -9 plus -1? I think it's -10. And then we'll have 0 here. And so now we see more clearly that the eigenvector for this situation is going to have the third entry is going to be any real number except 0. So let's write this down. The third one is k. The second one is 0 because -10 forces k2 to be 0. And then once the second one is 0, then the first one will also be 0. So this is the solution, and therefore the set of all eigenvectors, so the eigenspace, is the span. Of course, vectors of this form, with k not being 0, are spanned by a single vector. So the eigenspace is one-dimensional, and that's the vector 0, 0, 1. So if I'm just looking for one eigenvector, which I am in this case, for lambda equals 1, I just need one eigenvector. If I go back here, you see, I want one eigenvector for each eigenvalue, right? And so for lambda 1, I will pick just one eigenvector, and I can just pick this vector 0, 0, 1. So I can now say k1 equals 0, 0, 1. Now let's see what k2 and k3 are equal to. These will correspond to the eigenvalues -3 and 3 respectively, right? Okay. So let's have a look at k2. So this is for eigenvalue lambda equals, just to make sure I'm not going to make a mistake, let me go back here, it's -3. And putting that value in, we're going to have the following matrix. -3, -9, oops, sorry, no. Putting -3 into lambda will get, because lambda had a minus in front here, we get a 3, then -9, 0, then 1, and then again 3, 0, and then we have 1 minus -3 is going to be 4, right? So we can see here that it is now the middle row that's going to become the row of zeros. So I just multiply the middle row by 3 and subtract from the top row. So I'm going to get 0. No, sorry, wait. What did I say? I multiply. Well, I can multiply it by -3 and then add, right? And then I will get 0. I'm gonna get something strange. Let me check if I didn't make a mistake here. For that, I'm gonna go back to the matrix, -9. We had minus lambda. Okay, so the matrix had zeros there. Okay, great. All right. We're going to have here -9, 0, 0, and then 0, 0, 4, 0, which is very strange. I have figured out what was wrong there. To my great embarrassment, I made a little omission in writing out the eigenvalues. Of course, lambda squared plus 9 doesn't decompose as lambda 3 times lambda minus 3. It decomposes rather as lambda plus 3i minus lambda minus 3i. So I just forgot to put the I in there. Okay. Now that we've put the i's in there, that doesn't affect the first eigenvalue, but it does affect the other two, and now we were on our way here figuring out what the eigenvectors are. And by the way, how did I know that something that I had a mistake taking place here? Well, because looking at this matrix, what I was getting here was only the zero solution, and an eigenvalue by definition is something that's gonna give me a non-zero solution here. That's how we got the value for lambda. It's the determinant make equal to 0 ensures that the corresponding system will have a non-zero solution. And since I was getting only the zero solution, then I could figure out that, wait a second, I must have had a mistake somewhere. And then I checked the matrix A, and that was fine, and so I went to checking the eigenvalues once again, and that's when I noticed that I had a omission of the complex number I there. So putting it in, we're gonna have 3i here and a 3i here, and this is then going to be not 4, but instead it's going to be 1 minus, okay, so lambda 1 equals minus 3i as I understand. Let me check here. Yeah, so that comes from the first middle term there. Okay, great. And so we're going to have here 1 minus 3i, which is going to be 1 plus 3i, right? So that's what we have instead of 4. We have 1 plus 3i. Here we have, let's see what we have here. So now we want to multiply the bottom row by 3i, and then, well, maybe by minus 3i, and then add. And if I multiply bottom row by minus 3i, I'm going to get exactly the top row. And when I add them, I'm going to get a row of zeros, right? This times minus 3i is going to give me minus 3i here, and here it's going to give me minus 3i times 3i, and I times I is minus 1, so there's going to be plus 9, right? And then by adding the rows, the middle row is going to become 0. Okay, so that's the eigenvalue lambda equals minus 3i. And by the way, the fact that I mentioned here about different eigenvalues giving rise to linearly independent eigenvectors should still work, except that the geometry now becomes a little bit more complicated, because now the stretching by a certain factor is multiplying by a complex number, and so perhaps the geometric intuition behind this is no longer the valid one. But the fact is, the result is still true. At least I very much hope that it is. Okay, so let's see where we go from here. So we want to solve the system, and the third line gives us that the k3 should be 0. So remember that we're trying to find a second eigenvector. We just need one eigenvector for this eigenvalue, right? For each one we just needed one. So k2 is going to have 0 at the third one. The middle entry here has some flexibility. It can be any real number, k. But what about the first one? Well, if I divide throughout by 3, I'm going to get 1, minus 3, and 0. So then I see that the first one should be 3 times the second one, right? I'm talking about the entries in K. So this will be a solution of the system given here. For any K not being 0, but as I said, I only wanted one of them. So instead of calling this K2, I'm just gonna leave it like this without the label, and then I'm going to select one of them, and namely I will select the easy one when K is 1, for instance, 3, 1, 0, and that's going to be the second eigenvector. Now we are left to find the third eigenvector. And so let's go back to the matrix. It's this matrix we have here. And this time we want lambda to be, previously we had lambda equals minus 3i, and now we want lambda to be 3i. So if we take lambda equals 3i, then this matrix will become minus 3i, minus 9, 0, 0, 1, minus 3i, 0, 0, 0, 0, and then here we have 1 plus, sorry, no, it's minus 1 minus 3i, right? Okay, so let's see what row echelon gives here. We need to multiply the second row. We would want to multiply the second row by 3i and then add to the first row. And so we'll have a 0 there. And this times 3i is going to give us, because I squared is minus 1, is going to give us 9. And 9 plus 9 is 0. So we'll have zeros there. And just a moment. Sorry, did I make a mistake again there? Oh dear, I forgot about the I there as well. I'm very sorry about that. So we want to keep that I there, right? And then, so here we're going to have 3k times I, and not just 3k. And so here when we select one value of k, then we select k equals 1, we're going to have 3i, 1, and 0 as the eigenvector. Alright, then in here we'll have this situation, and that's going to give us a 0 in the third entry because of this thing here. So this is something times k3 equals 0, and that's something, then that k3 must be then 0 because this is a non-zero number. The middle row is going to give us flexibility in terms of what the second entry is, so we can call it some k. And what about the first one? Well, the first one will be, if I divide throughout by 3, we'll have minus I. Oops, I realize now I made another mistake. Okay, so if I, sorry about that. So if I go back here and write the corresponding equation out, I'll have 3i times k1 plus minus 9 times k2, right? And so that equals 0. So what we need here is k1 equals 3k2 divided by I. But dividing by I, since we can do this thing here, is the same as multiplying by minus I. So it's equal to minus 3k2 times I. So we have to put that minus in here, and so we keep that minus there. Okay. Now, coming back here, again we have any k value, and then we're going to have here 3i equals, so we carry this on the other side and do the same trick, and so the result will be that it's going to be, this time it's going to be plus, because when we carry it on the other side the signs will be opposite, but then carrying over I will result with the signs coming the same, and so we'll have it to be 3k, but the I should be there as well. 3k times I. Okay, and so then out of this we can pick out k3 to be one of the these vectors with one of the k values. So we'll pick one, a k to be equal to 1, for instance, so we'll have 3i, and then we'll have 1 and 0. At this point we are now able to write down the final answer, because we have the eigenvalues and we have the eigenvectors, and all we need to do is to arrange them in the matrices, right? So what are the eigenvalues we had? So that's going to be the diagonal entries of the matrix. These were, I think, 1 minus 3i and then 3i. So 1 minus 3i and 3i. And then we have a bunch of zeros here. And what about the matrix P? Well, for the eigenvalue 1, the eigenvector was 0, 0, 1. For the eigenvalue minus 3i, the eigenvector was minus 3i, 1, 0. It's an interesting coincidence there. Minus 3i, 1, 0. And for the eigenvalue 3i, the eigenvector was 3i, 1, 0. So you see how the eigenvectors, the order in which we put the eigenvectors, should correspond of the order of the corresponding eigenvalues. So the first column is an eigenvector for that eigenvalue being 1, and the second one is for the eigenvalue being minus 3i, and so on. All right. We then got that the inverse of P times A times P equals D. We don't really need to find the inverse of P, because as you saw, we got the P without knowing what the inverse of P was. But you might be thinking now, what if I want to check my answer is right? Do I then need to find the inverse of P? No, because this equation can also be rewritten like this: AP equals PD. So I just need to check this equality holds. The only thing is that I have to make sure that the matrix P is invertible. But that can be done by checking that its columns are linearly independent. However, as we said, if we have 3 different eigenvalues, that will automatically be so we wouldn't have to check that part. Okay, so just for the sake of really checking our answer, let us actually carry out the calculation AP and compare it to PD and see if the 2 products of matrices are going to be the same or not. Alright, so for that I'm going to copy what the matrix A was. Let's put it here. So that's the matrix A. I want to multiply that by the matrix P. So that's one thing I want to do. I want to find this product. Maybe I'll put it down here. And then I would want to multiply also the matrix P by the diagonal matrix. And then compare those answers, right? So that's the matrix P, and here is the diagonal matrix. And let's see what we get in each case. 0 times 0 and 0 and 0, so the first entry here is 0. Then now with this row, because it has non-zero entry only in the middle one, what we're going to be basically doing is in each column picking out the middle one and multiplying that by -1, right? So it's going to have 0, and then we can have -9 and n minus 9. Now with the second row multiplied by this matrix, which is what needs to go here, we'll have to pick out in each column the first entry and multiply that by 1, and so we'll have 0 minus 3i, 3i. With the third one, we just need to pick out the third. You see, in each column, we'll be picking out the third entry, because the first two are 0 in the first row, in the third row, sorry. So then we'll be just picking out 1, 0, and 0. Now, let's see what this matrix product is. And we already should know at this point that multiplying something by a diagonal matrix results in the same matrix whose columns are now simply stretched by the factors appearing in the diagonal entries. Of course, this is exactly why all of the things we explained here works. So behind this is one of the things behind this analysis of how the diagonalization problem translates to the eigenvalue problem is based on how we multiply a matrix by a diagonal matrix, but one can also directly multiply it out if one doesn't want to think about all those complicated things. Okay, so let's see. So the first column is going to be the same as the first column of the left-hand side matrix multiplied by 1, so we'll have 0, 0, 1. The second column is going to be the same, but multiplied by -3i. And -3i times -3i is -3 times -3 is 9. And then I squared is -1, so it's -9. And then we have to multiply 1 also by -3i, so that's -3i here, and 0. And the third column will have 3i that needs to be multiplied by each entry here. And so 3i times 3i is -9. And then we'll have 3i there. And then 0 times 3i is 0. And you see that by some absolute magic, I managed to get the right answer and didn't make any mistakes. At least any of those mistakes that were not fixed along the way. And so this confirms that our calculations are right. And we indeed get A times P equals P times D. Since the eigenvalues were different from each other, the eigenvectors will be linearly independent. And so we can be sure that this matrix P is invertible. If I don't believe in that, and if I want to check that the eigenvectors are linearly independent, or maybe they came from same eigenvalue in a different example and I actually want to know how to check that, well, we'd have to pick out the eigenvalues carefully, so it's just not as simple as that. It has a long story behind it, but let's say I've got already something written down, I'm just checking if the answer is right or not. Linear independence can be checked like this, that the first one must be a non-zero vector. These are the eigenvectors, right? So the first one is non-zero. The second one cannot be a scalar multiple of this first one, and it isn't, because the only way to get 0 at the bottom here is to multiply the first one by 0. But then if you do that, you're not going to get 1 and -3i. And then finally, that the third one is not a linear combination of the first two. The only way the third one could be a linear combination of the first two, let's see. So how can so if this whole thing is a linear combination of these two, specifically 1, 0 would have been a linear combination of 0, 1 and 1, 0. But that's the only way to achieve that is to multiply each by a factor 1, right? No, sorry, what am I talking about? So how do we, can we get 1, 0 as a linear combination of 0, 1 and 1, 0? Well, because we already have 1, 0 here, we need to have here factor needs to be 0, right? So the only way this third one could be a linear combination of the first two is if we multiply the first one by 0 and the second by 1. But if we multiply the first one by 0 and the second by 1, we're not going to get this vector. We're going to get that vector back, right? So we can see then that it's impossible for the third one to be a linear combination of the first two. Okay. That completes our task of solving a diagonalization problem for a specific matrix by means of finding the eigenvectors and eigenvalues of the matrix.